I am going to start lecturing. Hopefully you'll turn on your cameras because I can't see half of you, and that's kind of sad because I don't know what the hell you're doing. But anyway, I don't know. You could be doing awful things. But I'll just draw your card out of the stack repeatedly until your picture appears. And I see people showing up. That's good. Okay, this is weird because now I've got this light shining right up in my face, and whenever I look at my paper, it's like my paper's glowing, which is pretty awesome. You can kind of see it. Anyway, okay, so today is going to hurt a little bit. So everybody just go ahead and accept that. It's going to be painful. Part of it is I'm going to demonstrate the details of an argument that get us to a tool that we can use, but at the end of the day, I know what's going to happen. You're all going to totally forget about that argument, and you're just going to know and love that tool and use it pretty regularly, and that's fine. But part of the reason of going through the argument is to show you how we make use of some of the things that I've already shown you. And then at the end, it's going to be nice because you're finally going to see the utility of all of those wonderful traces of gamma matrices, which we learned and did homework on a long time ago. And you're probably like, why did we do that? Well, today you're going to learn why. Daniel, that's a pretty scary silhouette you got going on there. But anyway, okay, here we go. So I am going to start with the Feynman rules for QED. And the Feynman rules for QED, they are more complicated than the Feynman rules that we learned how to apply to the ABC theory, but honestly, they're not that bad, okay? The one thing that they're going to address, which I warned you about last time, was that because we're dealing with spinors and tensors for that matter, order is going to matter, at least we're talking about the spinors, but we'll learn a really nice, beautiful way to manage that through Spinor Sandwiches. But it's going to turn out that even after we get the Feynman rules down, we draw a diagram, we calculate M, the next step is going to be the pain in the butt. Okay? But I'll wait and I'll bring that to bear in a few minutes. So let's just get started with the Feynman rules. So number one, draw a diagram. And when you're drawing the diagrams, there's a couple of new important rules to bear in mind for things. First of all, you have to know whether you're dealing with a particle or an antiparticle. So you start by drawing lines, and these might be internal lines, they could be external lines, they're just lines in the diagram, and you label what particles those lines are associated with. So if you're dealing with electrons, then you put an E somewhere near the line to say this is an electron line. By the way, are the shadows making it hard to see the letters on the board? No? Okay, I can't tell. I just see my little picture in the thing. And all right, good. Now, as I mentioned last time, you've got to put one more piece of data on here to indicate whether you're dealing with an electron or a positron. And it's not that you call this P. Okay, we actually continue calling this an electron line, but what we do is we give it a flow. So if you have an electron and you have a flow arrow on the line itself, which is going forward in time because time is forward going to the right, to indicate an anti-electron or a positron, you put the flow line to the left. Okay? What if we have a photon, which is normally symbolized by gamma? What direction do you think the flow line needs to go on that? Chance. Are you here, Chance?
Yeah, I'm here.
Oh, there you are. Sorry. It's a large network of people. Chance, what direction do you think I need to put the arrow on the photon line?
Going out? Like...
This way?
No.
That'd be pretty awesome, but no.
Yeah, we're
What do you think?
I mean, I think like, the way the first electron you have drawn is.
Well, let me ask you a question. Do you think there's anti-photons?
No.
No, there's not. There's no such so actually what we argue is that the photon and the antiphoton are the same particle. You can't distinguish between the two. Okay? So therefore, when you draw photon lines, there's no need to indicate whether it's a photon or an antiphoton. So no need to put an arrow on that line. Okay?
Okay.
Now, that's a new ingredient, and then you have the old ingredients. So you label your momenta. So if this is an external line, you might put a P there. And if this is an external line, you might put a P there. And if this is an external line, you might put a P there. Notice the momenta always flow forward in time, even for an anti-electron. Okay? So this is why the arrow on the line and the arrow associated with the momentum, they don't always have to be the same. Okay? And then you also know that if these are internal lines, then you can choose the internal momentum to either flow with the object, or you might find yourself choosing the internal momentum to flow against the direction of time, and that's fine. For internal momenta, we don't have to be careful about that they have to flow forward in time. Okay? And part of this is, you've probably all experienced this, but you have, diagrams that look like this, where the internal photon is actually vertical. It's not actually moving forward in time or backwards in time. So when you want to label its internal momentum, it's good that it doesn't matter which direction it's pointing, because, is that pointing to the left or the right? I don't know. Okay? So with internal lines, it doesn't matter which direction you choose for the momentum. For external lines, though, the momentum always has to flow forward in time. Okay. All right, now, each external line gets a factor. This is vastly different than the ABC theory, because in the ABC theory we were dealing with particles of what type? Hunter. Is Hunter here?
Yeah, I'm here.
Nope, it's Hunter Thompson. Sorry.
Oh.
Hunter Thompson is not present. Okay, well, Hunter Leon, why don't you tell us? What kind of particles were we dealing with in the ABC theory?
We were dealing with massive particles, weren't we?
We were dealing with massive particles, but what type of transformation did they undergo in space-time? Were they scalars, spinors, or vectors?
Weren't they scalars?
They were scalars. And as such, if you know their momentum and you know their mass, you know everything there is to know about their dynamics. However, if you have spinors and you have vectors, these also have angular momentum, intrinsic angular momentum, or spin. And it turns out you have to say what that spin is doing. Is it spinning this way? Is it spinning this way? So that's what these factors are going to indicate for our external lines. What's the direction of their spin? Okay? And I'm just going to draw a nice picture here to show you how this works. So, actually, hold on. This needs to be a true bubble. So this is just some process, and I'm going to have 3 cases on each side. Okay? The first case is if I have a particle which is coming in. The second case is if I have what? Madison. What's going on here? Madison, you're muted.
What do you mean by like what's going on there? Like
What's going on right here? Is this a particle coming into the interaction or leaving the interaction?
It's going into the interaction.
And so if that arrow points in the opposite direction, what is it?
An electron? Or what do you're
So this could be an electron. What does this have to be?
an anti-electron?
It's an anti-electron. So this is when a particle comes into the interaction, and this is when an antiparticle comes into the interaction. Okay? Photons coming into the interaction. Now let's look at the possibilities here. We can have a particle leave the interaction. We can have an antiparticle leave the interaction. Or we can have a photon leave the interaction. Of course, we can have more than any of these on either side, but it's got to be one of each of these three. That's the only three possibilities we have. Okay? Whenever you encounter a particle entering the interaction, you want to write down a factor of U. If you have an antiparticle entering the interaction, you want to have a factor of V bar. If you have a photon entering, you want an epsilon lower mu. If you have a photon leaving, you want an epsilon mu star. If you have an antiparticle leaving the interaction, you want a V. And then if you have a particle leaving the interaction, you want U bar. Okay? Now, Hunter. Oh, no, never mind. It's the other Hunter, but we're going to leave it alone. Josh. Are you here, Josh? Josh. I don't see Josh.
Yeah, I'm here.
Oh, yeah, sorry. You're the big J down at the bottom. I think I recognize faces more than J's. What do you think these U, V bar, V, epsilon, what do you think those are telling us about? Eric,
They're telling us.
hold on, pause. Eric, stand upright. I'm never going to be able to recognize you while you're upside down. Carry on, Josh.
Yeah, Eric, get off the ceiling.
Carry on, Josh.
Those particles, are those just the particles that are interacting?
Are those just a part? So, well, no. I'm asking, what are these factors that I'm writing down? What do they tell you about?
I don't know.
Anybody want to help him out?
What you're writing because I have really bad internet for some reason right now.
Okay, does anybody want to help him out?
Yeah, can I phone a friend?
Yeah, Ross is answering the phone.
Yes, Ross.
Ross?
So those things, the U, V bar, epsilon mu things, they contain information about the spin of particles.
Yes. Yeah, so I don't know if you remember last time, but we talked about, the wave function of a particle having something like that. I might be a little bit wrong in that, but this part of it is just telling you about the momentum and its, displacement through space-time, whereas this factor is telling you about the spin. Now, the spin for relativistic particles depends on the momentum, and we saw that, early on in the semester. But these are just telling us what the spin states of these various particles are, and I'll tell you what we'll do with those a little later on today. Okay? So, now we're gonna, when we write these factors down, what we're gonna do is, when we're labeling the external momentum, so maybe I'm going to do P1, P2, P3, P4, P5, and P6. What you want to do is, in each of these factors, you just want to label what momentum it's associated with. And so we'll label them by putting the number of the momentum in parentheses. And you'll understand the value of this in a bit when I work through an example. Okay? So if I have a particle coming into the interaction and it has momentum P1, then I'll write U1. That 1 is just a label telling me which particle it is. Or sorry, which momentum I've associated with it. Okay? All right. For each vertex in our diagram, we get a factor of I times GE times gamma mu, where GE is E, which is the fundamental electron charge, times square root of 4 pi over h bar c. So obviously writing this is just avoiding having to write that combination of constants all the time. All right, let's see who we're going to victimize. Joel Bean. Joel Bean, what kind of object is this?
All right, let me make you bigger.
Whoa. Why am I dwindling small on your computer? That's bull. All right, what kind of object is IgE gamma mu? Is it a scalar?
No, that's not a scalar. Because, okay, wait. What is the lower index on G? Can you tell me that?
It's the coupling associated with the electric charge, which is so you could call it the electron charge. The muon and the tauon have the same charge, so we'll just refer to that as the electron charge. This factor will be a little bit different when we're dealing with quarks because quarks have fractional electric charges. But so we're just going to deal with electrons, muons, and tauons, and so this is just referring to, okay, for all of those you use the electron charge E there. So that doesn't mean anything. It's not a subscript of a space-time transformation going. So what is this?
Just a tensor.
It's a tensor?
It's a vector of matrices, right?
Yeah, calling that a tensor is shortcoming. It's a space-time vector, but each component of that vector is a matrix in spin space. Okay, so this is one of those hybridized objects that is non-trivial in both space-time and in spin space. Okay, if we wanted to indicize spin space, then we might put, a couple of spinor indices on this, but we're not going to use spinor indices. We're not going to use the index notation for anything spinorial. So you just have to keep that in mind. Whenever you see gamma, remember gamma is a matrix in spin space, in addition to, if you're talking about gamma mu, a vector in space-time. Okay. Now things are going to get a little more familiar, okay? Each internal line, and I want to remind you there's a difference between external lines and internal lines. Each internal line gets the following factors. If you have electrons or positrons, and I hope it's comfortable enough for me to interchange positron with anti-electron because they mean the same thing. A positron is an anti-electron. But if you have a positron or an anti-electron, then as we derived last time, the propagator is I times gamma mu Q mu plus MC over Q squared minus M squared C squared. Okay? Sarah, you awake? I know you're awake. I see you writing. What kind of factor is this? What kind of object is that? This whole thing.
Just a number?
No.
Yeah, because you're adding something in the numerator to MC, right?
Yes, and it looks like a number if you take MC to be a number, but we're leaving out that thing that we should always realize is there even though we never write it. What is gamma?
It's a vector.
Gamma is the space-time vector of matrices.
Yes, well, if the space-time vector index is contracted with q mu, is this combination a space-time vector or a space-time scalar? This combination of gamma and q.
Should it be a scalar then?
It's a space-time scalar, but is this a scalar in spin space?
No.
No, it's a matrix in spin space. So that means you should have the identity in spin space in front of MC.
Oh, okay, that makes sense.
So the important observation is that overall, this is a matrix in spin space. Okay? This is a matrix in spin space and a vector in space-time. You have to understand what is and isn't trivial in spin space, because you've got to be really careful with the order in which you write things if they are non-trivial in spin space. And we'll see this in an example. The algorithm here is going to get played out through the course of an example, so we'll get there in just a minute. If you have an internal photon, then you just write minus I eta mu nu over q squared. And Dylan,
Yeah.
what kind of object is this? The whole thing.
It's a space-time tensor.
Is it trivial in spin space?
Yes.
Yes, it is. Okay, so this is just a space-time tensor and it's trivial in spin space. What's nice is that means that this can go anywhere. It doesn't really depend on the order of things. Okay, because we're going to use index notation to make sure that, you know, things are combined in the right way in space-time. But in spin space, we're not going to use index notation, so we have to write things in the correct order. If this is a scalar in spin space, it can go anywhere in your expression you want. Okay? All right. So then we want to conserve momenta at all vertices with delta functions. That's the same thing we did in the ABC theory. At each vertex, you want to write 2 pi to the 4th times a four-dimensional delta function, summing all the momentum going in and subtracting all the momentum that's going out. So that's a step we've definitely worked with before. And then you want to integrate over all internal momenta with a factor of d4q over 2 pi to the 4. And maybe I'll just be a little more specific here, 2 pi to the 4 times the delta function. And then when you do the integral, each internal momentum in your expression gets a factor of d4q over 2 pi to the 4th, and then you can throw an integral sign out front. And then step 7, once you've done all of the integrals that you can do with the delta functions, that should leave you with an overall delta function that is acting only on the external incoming and outgoing momenta. So you cancel that and multiply by I to get M. Okay, that's the same step we did with the ABC theory. So the practice with the ABC theory is really going to play out. There's just going to be some extra ingredients in this spinor story. For example, when you have certain things coming in and coming out of your interaction, you're going to anti-symmetrize. So you're going to anti-symmetrize between diagrams, and I'll exhibit this, or I'll show you this in an example. So if I have 2 diagrams, and they can be related by switching certain things, then you have to anti-symmetrize their contributions to M. That means if one of them is positive, then you put a minus sign in front of the other one. That's all anti-symmetrize means. But let me show you the combinations. If you can switch two incoming electrons or positrons, okay, so what I mean by that is if you have two electrons coming in, and you have two different diagrams, and the way to relate them is just by switching these two electrons, okay? Then you have to anti-symmetrize between the contributions that each of those give to M. That means they have to come in with different signs. Or to outgoing electrons or positrons. Okay, so, you know, if you have an outgoing, actually let's do anti-electrons. And this is where it gets interesting. Or one incoming electron-positron with one outgoing positron-electron. Okay, so what this means is if you have an electron coming into the interaction and a positron leaving the interaction, if I can get that same diagram starting with another diagram and just reversing those two, then I have to anti-symmetrize between those two contributions. Or if I have an incoming positron and an outgoing electron and they're related by reversing those two. So we'll see an example of this when I'm actually doing some calculations, okay? So you can either have incoming electrons, outgoing electrons, or an incoming electron and an outgoing positron, or all of these other examples you get by looking at the right-hand side of the slash. Okay. Now, in all of this, all I've done is told you what you have to write down. I haven't said jack shit about the order. Okay? So ultimately, I got to tell you something about the order. In fact, I need to tell you about the order before you start writing stuff down. Okay? So, you want to make Spinor Sandwiches. God damn it, do you people ever laugh? It's so quiet, it's ridiculous. Unmute yourselves and laugh. Thank you. This is such a weird environment otherwise. Okay, you can go quiet again. Okay. I want you to make Spinor sandwiches. So, and I have this written in text in my notes, but it's really only something that's going to make sense if I work it out as an example. But I can tell you roughly how to make a Spinor sandwich. To make a Spinor sandwich, you either start with an outgoing particle or an incoming antiparticle. Okay? But you start with this and you basically follow its trail back through the diagram. And you write down this factor, then you write down the factor for any vertex that you hit, and then you will eventually come out this line. So this Spinor stuff and this is going to end up forming a Spinor sandwich. Because this is the adjoint of this, so U bar U together forms a spin space scalar. We can shove spinorial matrices in between them and that won't change the fact that this makes a scalar. Of course, if we start with V bar and have a bunch of spin matrices and then end with a V, then that's going to make a scalar as well. Okay? But like I said, you know, I'll illustrate that through an example that we're going to turn to now. So are there any questions about these rules as I've laid them out? Or are you ready to see this put to use? Jaylon, stand up straight. Okay, here we go. I'm going to erase all this. All right. Okay, so let's get our hands dirty with an example. And my first example is going to be E plus E goes to E plus E. That is, we're going to take two electrons, collide them with each other, and we want to calculate things associated with two electrons coming out. Okay? So take a moment. Remember the vertex with QED, everything has to be built out of this vertex. Okay? Where, of course, you could also do this. Take a moment to write down the lowest order diagrams that would describe this. And once somebody has them, shove them into the camera so I can see what you've got.
What the fuck?
Okay, so Dylan? Okay, so let me address Dylan's. Okay, so Dylan has this diagram. Okay? And he also has this diagram. Dylan, can you hold up your diagram really quickly? Really close. Okay, yeah, okay. All right. So this is actually not allowed because the vertices that you build quantum electrodynamic diagrams out of, they always have to have the flow of particle into the vertex and the flow of particle out of the vertex. Here you have particles flowing into the vertex. Or the matter particles, the electrons, both of them flowing in. So what you could do is you could reverse the order of this. But now this is an electron and an anti-electron coming in, which is not what we're looking for. So this diagram actually doesn't apply. There's nothing with this shape that applies. Did anybody come up with another diagram? Or is that the only one you can come up with?
Can you make a box one with this?
Well, you can definitely, but I don't think you need to. Because I want the lowest order diagrams, Avery.
Okay.
Trust me, after the homework,
Put up 4, yeah.
after the homework, you guys are masters at making the higher order diagrams. I totally understand and appreciate that. Good job. If I just want the lowest order, though, is there another one?
Can you just have it not interact at all?
No, so you always want the connected diagrams. You don't want the disconnected diagrams. So any other takers?
Could you have it that you have an electron and I guess it would be a positron coming in, but I get, never mind.
Okay, there's one more diagram, but I'll show it to you in just a second. Let me go ahead and label this one. No, I'm going to call that P2. call this P1. Call this P3. Call this P4. And, this is Q. Okay? I don't have to put an index on Q because there's only one internal line. I'll just call it Q. So I'm just labeling the momenta. But now I'll discover that there's actually another diagram.
I almost got it. It's just very hard to draw this in paint.
That's fine. Because remember, the specification of what's going on is that an electron comes in with momentum P2, an electron comes in with momentum P1, an electron leaves with momentum P4, and an electron leaves with momentum P3. However, this electron could actually come from this vertex, which means that this electron must be coming from this vertex.
Gabriel has a paint picture for you.
He does. Ah, there you go. Nice. Now, I have a question. Could I instead swap, or could I additionally swap the incoming particles and make a third diagram?
Wouldn't that be the same as the first one that you drew?
Well, no, it would be the same as this one.
If you swap both the first two and the last two?
No, sorry. If I swap the first two and the last two, yes, it's the same as this.
Okay.
If I swap the incoming particles instead of the outgoing particles, that's this diagram, because if you just take this and you twist it over without changing any of the external labels, you'd end up having the incoming particles twisted, okay? So these are the only two unique diagrams that we should consider, all right?
I just have a quick question.
Sure.
So sorry, so when you say the lowest order diagrams, in the ABC theory, that meant essentially a diagram with like 3 particles, like an ABC. So just
No. The vertices in the ABC theory were 3 particle vertices, but the lowest order diagram depends on what your in states are and what your out states were.
Okay.
I mean, right, if I'm doing A, in the ABC theory, this has to be connected by a loop of B's and C's. So you don't always have a tree diagram like these, where there are no loops in them.
Okay. And but on the homework, is it okay if we did like a single vertex diagram in the ABC theory, or is that what you wanted, or?
You're talking about in the second question?
No.
Well, Ross, everybody has their quizzes in front of them. I don't want to kind of talk about the answers.
Oh, sorry.
Yeah, we'll talk about it later.
Okay, sorry.
And I'll put the solution up. But let's just wait until you've turned those in. Okay, so now is the important part. If you've been sleeping, wake up. Because what I'm about to do is I'm about to employ all of those rules that I just wrote down to evaluate these two things. Okay? And you all know what I'm going to do. I'm going to evaluate this one, and then this one I'm just going to swap. Okay? So let me go through this. So first of all, we're going to do Spinor Sandwiches, and we're going to start with this outgoing electron. So this outgoing electron gets a factor of U bar. That's what outgoing electrons get. And I'm going to give it the label 3 because it's to be associated with the momentum of 3. Now if I follow this line in, I hit a vertex. So I write down the vertex factor. And then I leave the diagram going along this guy, which is an incoming electron with momentum 1. So that gives me a factor of U1. That's a Spinor sandwich. Pretty sweet, right? Avery, if you're going to do that, you have to unmute, man. Okay. All right. Next time anybody wants to clap for me, please unmute. Anyway, okay. So, why don't you write down this Spinor sandwich? Go for it. Is that what you wrote? Now let me ask you a question. Did you choose a different index for the gamma here versus the gamma here? You need to choose different indices, because if you use the same index, then it's kind of weird because they're repeated, which might mean you sum over them, but you only ever sum over indices when one is up and one is down. So that definitely is a no-no. Give these different indices. Okay? But there's a solution to that, because we have to write down the factor for the propagator here. And the factor for the propagator here is minus I times eta. And now if we're going to put indices on the eta, we can imagine we gave this vertex a mu index. We gave this vertex a nu index. So the metric connecting them should have mu nu. Does that make sense? This is important because in more complicated diagrams, you might have many internal photon lines, and you always want the indices on the metric that goes in the propagator for photons to match the indices you gave to the two vertices that it connects. So again, this is the mu index, this is the mu interaction vertex, this is the nu interaction vertex, so this photon should get eta mu nu, and then that's over q squared. All right. Now we want to conserve the momentum at the two vertices using the delta functions. So I've got P1 coming in, Q leaving, and P3 leaving. And then up here I have P2 coming in, Q coming in, and P4 leaving. And then I have to integrate over that internal momentum. And that's it. Okay? So this is important. When we did this in the ABC theory, we didn't care what order we wrote stuff down in, because everything we was writing was scalars, both in space-time and in spin space. Okay? Here, though, the order matters, but to get the right order, all you do is you make these Spinor sandwiches. All right? So if we, let me see which one I used. Yeah, so I will use this one to do the integral. So if I use this guy to set Q equal to P4 minus P2, then I'm going to be left with U bar 3 I GE gamma mu U1 U bar 4 I GE gamma mu U2 minus I eta mu nu P4 minus P2 squared. And then one more delta function, which now lovingly takes the form of the overall delta function, which conserves the external momentum. So if we want to get the expression for the final value of m, what do we do to this? Joshua Lewis is not here. Dang, where is everybody? You guys are driving me nuts. Oh man, look at that. Let me see if I can get this.
I thought we got to ask you a question when that came up.
Yeah, go for it.
Okay.
Yes.
I don't know. I just remembered that. Someone else come up with a question.
How was your studio this morning, Florida?
Oh, come on, you got to do better than that.
Well, you got to tell me how it was.
So, I did,
How many people did you have?
That's okay. All right.
Have you ever gotten in a car accident?
What?
Have you ever gotten into a car accident?
Yes, but never hurt. No. My studio started with some guy going, oh no, it was some girl's voice going, he's got a brain tumor. And then she very quickly turned off her microphone.
Wait, what?
I know. This was in a room full of people. She's like, but he's got a brain tumor. I'm like, okay, thank you for reminding me. All right, I'm just going to do this. We erase the overall momentum conservation. We multiply by I, and that is our M. Okay? Now, if we want to get this guy, do we go through all of this work again, or do we just switch things? What do you think?
Switch.
We switch, exactly. So if I call this the M1 contribution, to get the M2 contribution, we take the M1 contribution and we interchange the momentum here and the momentum here, okay? So I'm not going to write that down. It's this expression with the 3 and the 4 everywhere switched, okay? All right, now, these two things get combined to make M, but do I add or subtract them? What do you think?
I would say subtract them.
Why?
Because that you whenever you switch two of the outgoing electrons, you antisymmetrize it.
Yeah, look, how did we get to this from this? We interchanged two outgoing electrons. Or another way to think, maybe this is the way you should think about it. This diagram is this diagram if I switch these two, which is just unswitching them. So these two are related by the swapping of two leaving electrons, therefore they have to be antisymmetrized. So this should be minus. Okay? We good? All right, I'm going to pick up the pace a little bit. So we're going to leave this behind, and I'm going to look at another example. And Dylan, where are you, Dylan?
What's up?
You're going to be happy for this example. Haha. So let's draw the two lowest order diagrams for this example. Actually, let me just do exactly what I have on my paper. So All right, there's one example, and I'm going to go ahead and load up the momentum assignments. Okay. And now we can also do the following. Nope. Oh, shoot. Sorry. Minor correction. Okay, notice how all of the momenta labels for the external particles, they're sitting with who they should be sitting with. So here, P2 is the external momentum of the incoming antiparticle, and that's what I have here. Okay, P1 is the external momentum of the incoming particle, and that's what I have here. And then similarly for the outgoing. All right? Now, here's a question. Can I swap these outgoing particles?
No.
No. However, can I swap an ingoing antiparticle with an outgoing particle?
Yes.
Yeah, of course I can. But if I swap an incoming antiparticle and an outgoing particle on this diagram, am I going to get this diagram? Well, let's see. So I'm going to make this thing go out. And call that P2. This is P4. And I'm still going to have this one coming in. But I'm going to swap this one so that it's coming in.
That looks whack.
Oh no, hold on. This is an outgoing momentum. So this is P3 and this is P4. No, sorry. Right, this is P4 and this is P3. No, hold on. No. Just a second. Pause. Yeah, no. I want this to be P3 and this to be P2. Yeah, that's what I want. Okay? So this was just swapping these two, but you have to keep the same assignments of the external momentum. Now, is this diagram the same as this diagram? Yes, it is. I mean, the fact that you've shifted this above this and you've had the photon go up doesn't mean jack shit. It's just an internal photon. It can go anywhere it wants. It can go anywhere it wants. So literally take these two angles and just kind of pull them apart so that the photon is going crossways and you get exactly this diagram. Okay? So this diagram can be obtained from this diagram by interchanging an incoming antiparticle with an outgoing particle. Does that mean that we add or subtract the two contributions to M? We subtract. Thank you for your responses in silence. Okay? I'm not even going to go through and calculate the M contributions here. This is pretty much just like what we just did. Okay? So the point of this example is to show you this interchange that you can do. To actually get these factors of M looks very similar to what we did in the previous case. Okay? Are we good? You sure we're good? Okay, I'll trust you. All right. Now, I think I'm gonna lecture through this last. I mean, I have 3 more pages of notes, but I don't think I'm gonna do the last 2. I think I just want to get through this one, and then we'll cut loose. If I go past 6:15 and you need to go, that's fine. You can watch the video. But there's some. I mean, I gotta make room for what's gonna happen in the next lecture because I don't know if you remember. There's 2 lectures cut out of this course, so I've got to figure out what the hell I'm gonna do about that. But anyway, I want to start the story of, okay, what are we going to do about these spin states? Okay, so first of all, let me give you a very, very simple process which doesn't enjoy any of the symmetries. So if we're going to lowest order, there's really only one diagram that can contribute here. Okay, so I'm using an electron and a muon, and that way I can't interchange the outgoing or the incoming electron and muons. Okay, so this is the only diagram that contributes at leading order. At higher orders, there are plenty of diagrams. Okay, so if I go ahead and label my momenta, then
Alex, what were those noises?
there are people talking out in the hall. My front door's right there. It's literally 3 feet that way, and people are walking down the hall. Anyway, I'm glad they. I should have put myself on mute while I'm writing, but anyway. Okay, so here we go. You ready? So remember, you've got these U bars and U's and U bar and U, and if we really wanted to specify what we were sending in and getting out, I would have to actually tell you the explicit form of U and U bar, because remember, these have a spin up and a spin down possibility. So I could give you, for each UI that we see in here, and then if I have the expression for UI, I can form the adjoint just in the traditional way. But if I gave you how much of it is in the 1 state and how much of it is in the 2 state, and remember, this is largely spin up and spin down. So this might be spin up and this might be spin down, although, you know, whether or not these are eigenstates of SZ versus SP is of subtlety. But it's spin a half. You know, there's 2 spin states. So to specify the total state, you have to tell me the linear combination of spin up and spin down. So you need to know these coefficients, alpha I and beta I. Okay? And since the momentum has 4 components, you have to tell me what this scales like for each component. All right? Now, that is fine. If I wanted to say, I want to collide 2 spin-up particles, and I want to know what's the probability of 2 spin-down particles coming out, then I can say, you know, the incoming particles, I just use alphas 1 and beta 0. So for the incoming particles, which are 1 and 2, I would use just this. And then for the outgoing particles being spin down, I would use just this for 3 and 4. Okay? But we don't do experiments like that. It's really hard to control the spin of incoming particles, and it's really hard to detect the spin of the outgoing particles. So rather what we want to do is we want to say we don't know crap about the state of the particles going in, or more precisely, we want to say our expectation is that their spins are randomized, which means we should sum over the incoming spins and then divide by the number of states, which means we should average the incoming spin. And then when we're talking about what's coming out, we're not going to monitor whether they're spin up or spin down. We're just going to detect everything coming out, which means we should sum over all the spin states. Okay? So what I'm going to walk you through now, about halfway, because we won't get through it all today and we'll finish it next time, is how we actually do that with these expressions. Okay? So here we go. First of all, I want to just point out something generic. M, whenever we're doing a QED calculation and we have spinners involved, it always includes, among other things, a Spinor sandwich, that looks something like this. There's a U bar with some letter or some variable or some label A. This can be a matrix of spinners, which we know what matrix of spinners we encounter here. It's just IgE gamma mu, or a matrix in spin space. They're more complicated versions, but we won't worry about it right now. Times a spinner, and so this thing altogether makes a scalar in spin space. And now what we're going to do is we're going to go ahead and we're going to consider how this contributes to what we actually need for the calculation, which is not just m, but rather the magnitude of m squared. Okay? Because going through the magnitude of m squared is going to allow us to actually do the averaging using some of those expressions I gave you last time. So first of all, if the magnitude, or if the matrix element m contains a term like this, then the magnitude squared should contain something like this. Right? Because this is going to take everything in here and multiply it by its conjugate. So we're going to get this term times its conjugate. But I put a different label here than here. And the reason for that is because in case this carries a vector index like the mu, we want to make sure we give it a different index here, because if we get a gamma mu here and a gamma mu here, we don't know what the hell to do with two gamma mu's in the same expression. So this is just telling you, change all the space-time indices on the stuff that appears as part of your gamma, or as part of your spinorial matrix. Okay? All right? So, here's something cool. What kind of quantity is that object in spin space?
Scalar.
It's a scalar, right? This is an adjoint spinner. This is a spinner. When you combine an adjoint spinner with a spinner, you get a scalar. If you stick a matrix in between them, you still get a scalar. Well, that means that I can freely transpose this because it's a scalar. Transposing a scalar doesn't do anything to it. But if I transpose it, then that turns the star into a dagger. Okay? But this affords us something, because now that this is transposed, we can ask, if I have a product of three things and the product is transposed, how does that reduce to the transpose of the individual objects?
Switches the order.
It reverses the order, okay? So this is actually now going to be UB dagger, gamma 2 dagger, U bar A dagger. Okay? All right, and now we're going to work with this a little bit. So first of all, UB dagger, gamma 2 dagger, times. Now let's remember how we form the adjoint of a spinor. We take the spinor and we apply gamma 0 and then we dagger the whole thing. Okay, so this thing right here is our adjoint of U of A. It's U of A dagger gamma 0. This dagger is that dagger right there. Okay, we good? Yes? No? Possibly? Maybe? Okay, I see nodding heads. That's excellent. Now we're daggering a product of things, which means, of course, we can reverse their order and dagger them individually. That's pretty nice. Okay? And now what I'm going to do is I'm going to insert one of my favorite forms of 1, or the matrix 1 in spin space. What's your favorite form of the matrix 1 or the identity in spin space? Yes, exactly. Remember, gamma 0 squared is equal to the identity. So I can insert a gamma 0 squared here, and then I can remind myself that gamma 0 dagger is equal to gamma 0. Okay? So this is going to boil down to UB dagger, gamma 0, gamma 0, gamma 2 dagger, gamma 0, U of A. Now are you ready? I'm going to pick a card here. Ross, you awake? What is this thing right here?
U bar B.
Yes.
U bar B.
Remember what I told you up here? Well, that's what we've got here. So this is U bar B. So I'm going to take this thing and define it to be gamma bar of 2. Okay? So gamma bar is the gamma daggered and then surrounded by gamma 0. So this is a definition. And then we have U of A. Now that is just rewriting this term. But that is a very advantageous rewriting, because this means that M is going to have factors associated with U bar A, gamma 1, UB, U bar B, gamma bar 2, UA. Okay? And now is where we're going to do a trick. All right. Now, whether we're averaging over the spin states or summing over the outgoing spin states, the first thing you have to do is sum, right? I mean, when you're averaging, you just sum and divide by the total number. So let's start with a summation over the possible spin states associated with particle B. Whether it's incoming or outgoing, it doesn't matter. We have to sum. All right? Does anybody know of an expression I can use to describe this?
completeness relations?
Yes, exactly. This is the Spinor completeness relations, which is one of the things that I gave you Tuesday. So this is going to be gamma mu, p mu, plus mc, which we usually just call p slash. P slash is gamma mu, p mu. Okay? So now what we've got is that guy right there. All right, now let me reiterate what we're dealing with here. In spin space, this is an adjoint spinor, which means it's a row spinor. You would write its elements this way. This is an ordinary spinor, which means you would write its elements as a column spinor. What is this thing in spin space?
It's a matrix in spin space.
It's a matrix. Okay, and this is our usual, fundamental, a row vector times a matrix times a column vector gives me a number. Okay, so that's cool, that's good. Here's something interesting though, which you might or might not have known. Here we have row times matrix times column, which equals a number. But it turns out that that can also be expressed as the trace of the matrix times the column times the row. How many of you have seen that before? Interesting. Okay. Well, this turns out to be true for any matrix of column, row, and matrix form. All right? But now that means that we can take this combination and we can rewrite it. And we'll get the following. Oh, sorry. This is now sum over SB of m squared. Because when I replace this by this, I'm doing the sum over the spin. So this is not m squared, but it's the m squared with the b spin states summed over. Now I can take this and I can rewrite it using this fancy trick as gamma 1 PB slash, sorry, this should be B, that should be B, plus MBC, gamma bar 2, U of A, U bar of A. All right, this is the matrix. This is the column, this is the row. Matrix, column, row inside of a trace. Seems pretty reasonable, right? Why did I rewrite it like that?
You got UA and U bar A next to each other now.
Exactly. So what can we do with UA and UA bar? We can use the sum over spins. So now, if I sum over SA and SB for m squared, all right, then my expression is going to become okay? All right, so the bottom line is, whenever your matrix contains a Spinor sandwich, remember this is just one Spinor sandwich here. There's two of them in this amplitude. But for each Spinor sandwich, when you think about the contribution that it gives to the square, or the magnitude squared of the matrix element, you get this thing. But you can take this and you can immediately replace it with this thing right here, as long as you are willing to sum over the spin states involved, which you have to do anyway, because in experiments we average over the incoming and we sum over the outgoing. So we're always going to sum over spin states. All right? Does this make sense? Sort of? Kind of? Okay, good. So just to give you a hint, because we'll go through it next time, this is the trace of a matrix in spin space times this thing, which is not in spin space at all, times a matrix in spin space. What do you think those matrices in spin space are going to be composed of? Where are we going to get matrices in spin space?
Gamma matrices.
From the gamma matrices. So when you're evaluating this trace, ultimately you're going to be doing the trace over a product of gamma matrices. And if that doesn't ring a bell, you should review your homeworks, because you did an entire assignment studying the traces of the gamma matrices. Isn't that awesome? We're actually going to use that shit that we learned a long time ago. All right, that's it for today. Are there any outstanding questions?
I do just have one question. This might be pretty stupid, but with the P slash plus MC, isn't that still a matrix in spin space?
Well, if it's a matrix in spin space, it's just the identity. So that won't really contribute.
But the P slash, the P mu could have like different.
Oh, I'm sorry. No. I'm sorry. You're totally right. That's the danger of writing P slash, is I forget there's a spin matrix there. You're totally right. P slash is defined as gamma mu times P mu. This is a spin matrix. So this is a spin matrix plus the identity, which means a non-trivial contribution. But look, if we multiply all this out, we're going to have a term that's the trace of a bunch of spin matrices, or gamma matrices, plus a term that is the trace of a bunch of gamma matrices, plus a term which is a trace of a bunch of... So the trace of gamma matrices is what's going to save you in evaluating all this. And we'll see that explicitly next time. Okay? Other questions? We good? We sure? All right, now I'm going to give you a homework assignment to kind of flesh through a lot of this, but applying the Feynman rules to diagrams is obviously, once you get used to it, it'll be fine, okay? And once you see how this step finally ends, what you're going to realize, and we'll go over this next time, is that in calculating this to the end, because this involves, look at this is trace over spin matrices. If you trace over spin matrices, what kind of spinorial object are you left with?
Scalar.
You're left with a scalar. This thing is just going to be a number. What we're calculating ultimately is the probability or the lifetime of something. It can't be non-trivial in spin space. It's got to be a number. So this trace right here is one of the key steps to getting rid of the spinorial things and just producing a number. Okay? All right, I think I've lost about half of the crew, so let's end there. Don't forget to send your homework quiz to Levi, and I will see most of you next Tuesday, some of you a little bit sooner. All right? Peace out.